Welcome to the APL quest. See APL Wiki for details. Today's quest is the 8th from the 2016 round of the APL problem-solving competition. We're giving some numbers, and we need to return a two-element list. The first element contains all the negative values, and the second element contains all the non-negative values. We can do this by filtering the values. So let's start with making some values. Okay. APL has implicit mapping over arrays. That means if I make a comparison, like where 0 is less than or equal to these values, then it automatically compares all the values. Also, 1 and 0 are used as true and false. They are actually the same. We can use this to filter using this slash. We're filtering v. And similarly, we can filter v for the values that are less than 0. Okay, now we just need to put these two formulas next to each other. This is an expression for the solution. Let's make this into a function. We put braces around it, and this makes this an anonymous lambda, also known as a defin. We put v over here, and inside this we represent the argument with omega, which is the rightmost letter of the Greek alphabet, because the argument goes on the right. And so this is one solution that we could use, but it has a lot of parentheses and even inside these braces, and it's a little bit hard to read like that. So I prefer avoiding the parentheses. Now that means I need to have something like the slash that takes the arguments in opposite order, that takes the mask on the right and the data being filtered on the left. There isn't such a function in APL, but any function can be modified by this modifier or operator called commute or swap, which binds together with the function, the slash function, and creates a new function which is exactly the same but with commuted or swapped arguments. So now we can take this mask and put on the right and take the data on the left, and since APL has long right scope, in other words, we start computing at the right end of an expression, then we don't need parentheses around this part of the expression anymore. And we can do exactly the same thing over here. So this is another solution. One thing that's a bit of a pity is that we're comparing all the elements, which could potentially be many, twice. And we could actually infer the result of one of these computations from the other. So let's say we save this as the mask, and we can do that inline. The result of an assignment in APL is always whatever the value that's being assigned is. So now we have m available, and we continue to the left, and we can use m over here. But we need to negate it, because we want all the values that are not those. So this also works. We can actually get rid of this swapping, simplify things a little bit, if we had a positive mask instead of a mask we need to negate. It would be like this. But then that's not this. Then we need to make the opposite comparison over here. And then we need to negate it over here before we apply it. So this also works. We could also just take this mask and put it in a separate statement first. Diamond is the statement separator. It's strong like a diamond, separating things into parts. And then we could write it like this. Or we could say that this is the negative mask, and then we could have a separate positive mask if we wanted. And then we could write it as positive mask over here for symmetry. Oops. Oh, the negative mask, of course. There we go. Notice how APL points me at the name and tells me which name it is that's missing, so I can do something about it. And so this is another solution to the problem, which kind of looks nice. Finally, let's make a little bit of a variation on this based on set computations. So we're going to start by computing the positive values this time. And we do that as we did before. But now, instead of saving the mask, we're saving the values themselves. And the return value of this assignment, of course, is that value. Then the negative values would be all the values except the positive ones. And we can express that as all the values without the positive ones. So this tilde, when it's used with arguments on both sides, it means without. And when we used it with an argument only on the right, it means not. So how are these connected to each other? We can remember this by thinking of without or set difference as but not. So we want all the values of the argument, but not the positive values. Whereas here it just means not. And that's our final solution to the problem. Thank you for watching.